not only, but I will mainly start by talking about SL2Z as a subgroup of SL2R, and also I hope to talk about the group structure of this thing itself. Well, the term that I want to prove in mind is that SL2Z is a lattice in SL2R, namely, if it is discrete and of cofinite volume. So the coset space has a natural measure on it, and this measure is finite, or finite invariant measure. Throughout, this would be G, and this would be gamma, so the claim is. We know, and maybe I will also talk about it just a bit later, but Biel explained this at the tutorial yesterday. G mod gamma has an invariant measure on it. Sorry? Oh, thanks. On it, so what we really need to establish its finiteness. This is what we are after, at least in the first part of the lecture today. Probably many of you are familiar, and we explained yesterday, in any case, the structure or the theory of invariant measures on homogeneous spaces. But let me just recall this particular case where gamma is discrete. We also know that gamma is discrete. It's very clear. So let me just make one remark about the case where the group, the coset space of a group modulo a discrete subgroup. Then let me give a picture of it. If this is G, and what we can find always a fundamental domain. For the right action of gamma on G. So this is actually a presentation of gamma as a set, F will be the fundamental domain, times gamma. So that the map, the product map, that is an isomorphism. So every element in G could be presented uniquely as an element of gamma times, on the right, an element of this set F. If you wish, you can also think of this, if we have this natural map, G to G mod gamma, F is the result of a choice of a section of this map pi, and F is S gamma, S of gamma. Now pictorially, I'm having G here, and I guess that my picture is kind of a billion, but we should ignore that. And gamma act on the right, and this guy is f over here. And these are translate of f by element of gamma. Now, G act on the left on this picture. This is the action of G on G mod gamma, so we may view I better say, this what I'm saying now is kind of a parenthesis. It's a remark about how to think of such spaces, G mod gammas. It's not a real part of my lecture. Just some remarks. So we may view the action of G mod gamma as an action of G on F. We identified F and gamma, but how does G act on F? For x in F, G dot x will be, well, G times x. This is a group element, but it may not be in F, but there is a unique gamma that brings back to them. Maybe take a point x here, and it has its image gx in here, and there is some gamma such that this point is gx gamma, or gamma inverse. Depends. This is choice of conventions. So I will declare this point to be g times x, and this defines an actual action of G on F. This is the action borrowed from the natural action we have on G mod gamma. Times some gamma. This gamma actually is denoted many times by alpha gx, and one notices that this function alpha satisfies some cocycle relation. This is the cocycle. The structure cocycle of the pair G and gamma. And now maybe just to add to this picture, now if I take this fundamental domain F, and if I take little g here, and I apply to it, since my group is not assumed to be a billion, it has the image of F under G has nothing to do with this nice structure that I see from the right action of gamma on the space. It will be, I don't know, distorted in a certain way. This is G of F, this bubble over here, and well, this is Gx again. And I will use, well, this piece over here. Of course, G conserves the Haar measure, so the measure of this bubble should be the same as the measure of F. And when I bring it back, say this piece with little gamma, it will be something. Oh, I guess I shouldn't. There is no line here. It is a copy of this piece in the fundamental domain. Gamma brings this back to that piece. And if G is unimodular, as is in our case, the action of little gamma, this is little gamma, takes this copy of F to that copy of F, to F itself, and it brings this domain to that domain, and the action of little gamma on the right does not change the measure on the group G, as G is unimodular. So this process preserves the measure. So this action of little g on F is kind of putting it to pieces here, bring it back over here, and it preserves the measure. Okay? So the measure is preserved. As or if G is unimodular. The right and left Haar measure are the same. 14. So again, these are things that Miel discussed yesterday, but now I just want to make it very explicit in our situation, the situation where gamma is discrete. And why is SF2R unimodular? I mean, it is unimodular. Can you explain this? One explanation could be that it is a simple group, or it equals its own commutator. And maybe we'll see this later. Okay. So let me recall things we've done yesterday. We defined X to be the space of unimodular lattices. Another use of the same word, lattices in R2. So unimodular here means of co-volume 1. And we explain why this is isomorphic to G mod gamma. So this is the way we think of our coset space, G mod gamma. We've seen, also we discussed in details, the coset space G mod U, which is R2 minus 0, where U is the group of matrices with the following form. Maybe I better say T is in R, because I might consider U over other things later on. So this is the stabilizer of the vector 1, 0 in R2, and we have seen that there is some duality going on between G mod gamma and G mod U. I will now consider a different aspect of that very same duality principle, and I will consider something called Siegel transform, which is very close to the concept of Eisenstein series, if you are familiar with representation theory of SF2. So we have these two spaces, and in order to view the duality between them, maybe it helps to think of a common father, common mother of these two. So this is lattices. This is vectors, non-zero vectors in R2. So I want to find a common father, so let me give a name to it, Y here. It will be the space of pairs, unimodular lattice, that is an element of X, and a primitive vector. Of that lattice. Take all such pairs. A primitive vector in a lattice, we discussed this yesterday, is a vector that is not an integer multiple of any other. Obviously, we have this map on the right. Y to X. Forget the vector that you choose. But also I can forget the lattice. I can recall just the vector. This is an element of R2, a non-zero element of R2. So this is R2 minus. In group terms, this is, well, this is G mod U on the left here. Maybe G mod U R, let me emphasize this. The real points over here, G mod gamma, sorry, G mod U on the left, G mod gamma on the right, can we describe Y as a coset space to complete the picture? So if my lattice was the standard lattice, so G acts on all lattices, right? Transitively, on all unimodular lattices, transitively, we realize that. I can take my unknown lattice to the standard lattice, Z2. I still have the freedom of using an element of SL2Z at that lattice. I'm taking that pair and I'm trying to standardize it. To take it by a group element to the standard lattice, and the standard, this is 0, this is E1, and the standard primitive vector, E1. Okay? So take your lattice by an element of G to the standard lattice, you can do that. You still have the freedom to act by SL2Z on that standard lattice. SL2Z is a stabilizer of that lattice. And any primitive vector here I can take by an element of SL2Z to that primitive vector E1. This is my base point. So G acts transitively on that space. And what would be the stabilizer of that pair? The elements that do stabilize that lattice, elements in gamma, so Z points, integer valued matrices, which stabilize that vector. So they are in U. Actually, this is U intersection gamma, right? Or if you wish, the Z points in U. Is this picture make sense? Actually, also, if you like this language, I could, instead of writing gamma, I could write GZ. This is the Z points of Z. This is the language of algebraic groups I'm using here. And okay, that's very nice. And Siegel transform is, I'll be more specific in a minute, but takes functions over here, some function on R2 or R2 minus 0 to functions. So you take a certain space of functions on R2, two functions on X. So in order to do this properly, I better understand the structure of that map. So we have this.
Could you be more specific what do you mean by functions?
Yes, I will. So we have this general. Actually, I'm adhering now to general principles, but I will be also more specific about. I will describe this space as a fundamental domain, as a space very explicitly. But now let me stay a bit abstract. I don't really understand this space or that space geometrically now, but it is enough for me to argue analytically. So let me recall this general observation that we had. So if we have G mod H, now this is kind of a general setting, G act on this coset G mod H, we always had a commuting action by N mod H, where N is the normalizer in G of H, right? And if you mod out that action, if you mod this N mod H, take this space and take the orbit space with respect to that action. Since this action, this group acting, was commuting with this group that was acting, G will still act on the quotient space of this by that. So, and since the action here is transitive, the action will be transitive. It will be some quotient space of G again. What will be the stabilizer of point of the base moment? So this is a very general observation. And again, maybe in a few minutes we could make it more concrete here. But let me just leave it at this as is, and let me try to understand the group of automorphisms of this G space. So this is acted upon, so we have the G acting here, and here we are acting by the normalizer of this group in G, which is so can you see that, okay, U here, U there, is an abelian group, UR, and UZ is a subgroup of it. So definitely UR normalizes UZ. Actually, it is the normalizer, the full normalizer. I leave it as an exercise to you, but I'm not using it. So I'm saying that this guy over here acts. So there is, this is just a C. This is R mod Z, a compact group. That is acting over here on that space, and the quotient space will be that. So this tells me something about that map over here. So this map over here is, I mean, the fibers here are just circles. This map is proper map. This means that the play image of a compact space here, so a compact set here, this is a locally compact space. Not compact. A compact set is a bounded set that is also bounded from infinity and 0. And the play image of a compact set here will be a compact set here. I didn't describe much the topology of Y. It has a natural topology. It is a quotient space of G. I didn't explain what it is. One can do that. It's not so hard, but I didn't bother doing it. I didn't explain the topology here. There is some topology, locally compact topology, which I didn't explain again. But I do know that this map is proper. So if I have a compact set here, the play image of it will be a compact set here. And now, this means that if you have a compactly supported continuous function on this function in here, I can put it back to a function. I can pull back to a function on here, and it will still be completely supported continuous function. Furthermore, I can push this function down from y to x. So if you have a function here, so I can just, the fibers of y over x are just countable, right? A typical fiber is look like gamma mod uz. Right? A typical fiber is like SL2Z mod this one, right, N here. And I can just take this function that I'm getting here and estimate the values it has over the fiber and sum. Summation over fiber. In a minute I write a formula for it, and it will be clearer than this abstract. thing here, but this is a general principle. One can pull back functions and push them down, and if, very explicitly, if we had started with the function f here, going all the way here, so we'll write down the formula, I will get a function which I want to write down together, let's call it f hat. This is a Siegel transform. Which I can evaluate on lattices. Here's a symbol for a lattice. A copy of Z2 in R2. What will be this? What will be the formula for f hat? Explicitly now. It will be the summation of f. I have f. F is a function on R2. It is defined on vectors, which I want to view as primitive vectors of lattices, varying lattices. So here is the vector x. And the summation here is over the primitive vector of this lambda. So this will be the value of the new function at lambda. So just check that what I described, I mean, I could have just written down that formula for you. But by my description, my abstract description, one sees that starting with a completely supported function here, I end up with a function on the space of lattices, which I don't know very much now, but it is a completely supported function. The support, of course, will be just the image under the continuous map, y to x, of the compact support in y. The support in y is compact because of properties. Fine. So again, this is Siegel transform, and now come this brilliant observation that I can dualize this. The dual space of those functions is a space of Radon measures on X, and there is an invariant Radon measure on that space, which I know from general theory. There is an invariant measure on G mod gamma, which, well, I don't know whether it is finite or not, but it does exist. So G invariant measure on G mod gamma, think of it as G invariant functional on CCX, and this gives us by composition, by recomposition, a functional on that space. Take a function here, apply that map, and apply that given functional. So I'm getting now G invariant functional on CC R2 minus 0, which is by this a G invariant measure. On R2 minus 0. G is SL2. R2 minus 0, G mod U if you wish, as an invariant measure, as a unique one up to scale, right? We know it from general theory. G is unimodular, U is unimodular, but we also know it from our daily experience. There is a name to that measure, and it is the unique measure on R2, which is invariant. The unique measure on R2 minus 0, which is invariant under SL2, R is, please? Area. Or the measure. Thank you. The area measure.
No, it's not contained in that.
Oh. This is up to scale. Also, this is up to scale, right? So we must have gotten, we've started with some unknown measure. Actually, this is the measure we want to say something about. We got something known by using this transform. And now I want to be able to use our understanding of that Lebesgue gave us in order to shed some light about this unknown measure. So maybe before this, let me state the corollary. So this is analytic corollary. Actually, so we had, no, maybe just writing down this set of equivalences, one sees that if you take a function f on R2 and you integrate f on R2, or R2 minus 0 to say, it would be the same as integrating f hat on G mod gamma, on X, right? For every compactly supported continuous function. Now, just by completion, this is for every L1 function on R2 minus 0, or R2 minus 0. For the general, for the standard Lebesgue measure. So this is Siegel formula.
Generalizes from continuous compactly supported functions to L1 functions.
So this is an isometry between these two spaces. The Siegel transform is an isometry between these two, dense subspaces in those Banach spaces. So it extends to the completion. Okay, and now let me give you a very nice claim. I will explain this one, but take a specific function in that L1 space. Take the characteristic function of a big enough square, say the 2 by 2 square. This is 4 by 4 square. And transform it. And I claim that this is bigger than 1. I will prove this claim, but first I will explain what this claim gives me. Claim implies that the volume of X, by the way, when I say the volume of X, I guess that I used I picked in my story here a normalization of that volume. The measure, the invariant measure here is defined up to a scale, and I pick a scale such that this equation will hold. Such that here I will get the Lebesgue measure, not up to scale, right? So there is a choice of scale around. So this is the volume I'm using here. The volume of X, well, is the integral of 1 over X. And this is smaller, certainly, than the integral over X of this function, let me call it F now. Which is the same as the integral of f over R2, which is, who can compute fast? 4 squared. This is 16, which is less than infinity. And this is the proof of the theorem, right? What is the theorem? Here? No? Did I write the theorem? Ah, yes. Over there. Oh, more to that thing. cheated? You fine? Excellent. We have, okay. So I need to prove the claim for you. And there is a theorem, very nice one, that probably most of you do know, by Minkowski, that I want to state before. This is not about general lattices. This is about general convex sets. Let C, a subset of R2, be a convex, symmetric. Symmetric means C equals -C. Symmetric set with measure bigger than 4. Then, if you take C and intersect with a standard lattice, you get more than what you should get anyway, 0. Every symmetric set, convex symmetric set, has 0 in it. But if the volume is big enough, you get another lattice point, standard lattice point. Now I can either prove that theorem, which is very nice, or explain this piece. Let me do that first. Let me explain how we prove the claim, how Minkowski proves the claim. Minkowski implies that for every G in G, G inverse, take this is C, take -2 square, apply G inverse to it, this preserves the volume, the Lebesgue area, this is an SL by element, so the determinant is 1, it preserves the volume. So this is obviously a convex, preserves convexity, preserves symmetricity. This is a convex set of volume bigger than 4. And if I intersect it with Z, I'm getting more than just 0. Now, instead of doing Minkowski, which varies the set, but pick the standard lattice, I can just change the way I'm trying G, so explicitly. So -2 square intersect every lattice, and this is a generic lattice, not trivial. So chi of that set, when I apply,
You don't need the full power of Minkowski.
I don't need the full power. In Minkowski, I just what is the transform? I did. So I wrote explicitly a Ziegler transform for you, and this was summation on primitive vectors. And if you take that chi over there, in that domain there is a primitive vector. So this explains the claim. Okay, fine. Very nice. And now the claim of the proof of Minkowski theorem, which probably you've seen, but In any case, it is very nice, so I'm not doing it. So take such a C and take half of it and do, I also read that one. Probably. And do exactly what I did on that board and move it into the fundamental domain. Map it to 0, 1 square. So let me put a picture on the board for you. If this is C, and if this is half C. Oh. Sorry. This is C. Say this is the fundamental square. I can take this piece over here and move it to here by translation. I move everything by translating using Z square. This is using Z square translations. And the fact that this piece is a fundamental domain for Z square. I will take that piece over here and put it over here, etc., etc., etc. And by this, I suppose, maybe I will fill the box, maybe not. But this map, the map, is not injective. Right? By this assumption. Okay, not injective. This means that there exist x and y different in half C with the same image. And this means, well, 2x is in C, also 2y is in C, also minus 2y is in C, also the complex combination is in C. 2x plus minus 2y over 2 is in C, but this is x minus y, and this is in Z squared, and not 0, they are different. Okay. By this I did prove everything I promised. This is a lattice. I gave full proof. Maybe well, I didn't give all details somehow, but maybe the one thing I didn't prove, and maybe I will touch later, is simplicity, essential simplicity of S and T, which probably you do know. But now, what I want to do now, maybe wait. They told me to wait 10 seconds for questions.
Yes, a historical question, and probably there are various proofs of this theorem.
Oh, this is my next remark.
Oh,
I will discuss it. Thanks.
please.
Yes. I think that this proof that I gave is by Siegel, I guess, but the first one to prove the fact, the latticeness of SL2Z is Minkowski. Maybe Lennox. maybe you know other proofs. Why I did give that proof is that you can use just the same proof, essentially, to prove that SL and Z is a lattice in SL and R. So maybe I should say it for them. There is, you should beware for n bigger than 2, the map, and I'm introducing on my way notations which are, I hope, clear, yn to xn, the space of lattices in the n Euclidean space, and the space of lattices and primitive vectors on them, and you have the natural map, is not proper. So that was a funny way out that
So x2 is R2 minus 0.
no. No.
Is that
Oh, sorry. Thank you. It's that piece over here will not be proper in general. The fibers are actually so the fiber here was R mod Z. Can anyone think and tell me what the fiber will be for n equals 3? Can anyone identify the fiber? So you should replace U by, not by unipotent group, but by that group. And the fiber will be the real points of that group over the Z points of that group. So it will be SL and R semi-direct